All right, so welcome to Engineering 270. So I want to briefly review what we were doing in the previous lectures, which was we were talking about the interrupt subsystem. And I want to go over this briefly because it's very similar in spirit to what we're going to be doing in this lecture, which is talking about timers. A lot of the challenges of working with timers are similar to the challenges of working with interrupts. So let's do a really quick overview of the interrupt subsystem that we talked about before. So remember, the idea of interrupts was, what does a computer do? It does fetch, decode, execute. That's its whole life. And under normal circumstances, fetch an instruction, decide what it should do, and then do it. Fetch the next instruction, decode, do it, and so on. Now this fetch is normally from program memory. Whatever the program counter is pointing to, right, whatever instruction is addressed by the program counter, that's the instruction that gets fetched and then decoded and executed. So this program counter, this internal register, says what's the next instruction we should execute. And normally, at the end of each instruction, well, by the end of each instruction, the program counter is incremented by 2. When you do a reset, like when you first apply power to the PIC chip, the program counter gets set to a 0. So that's why after a reset, the first instruction that gets executed is an instruction at location 0. Because the first thing the system does is say, okay, what's the program counter? 0. Let's fetch the instruction from program memory location 0. Let's decode it, let's execute it. And in general, after that, it will add 2 to the program counter, and now it will fetch the instruction at location 2, decode it and execute it, and so on. And this process can be changed by things like call, go to, and so on, which do their own changes to the program counter. For example, if you say go to 1000, what that does is load the number 1000 into the program counter, and the next time that you do a fetch, it's going to read program memory at location 1000. That's how branches work. Same thing when you do a return, it'll pop a number from the stack, load it into the program counter. And of course, if our instruction is longer than 2 bytes, if it's something like a move FF or a call, this could be PC equals PC plus 4. Okay, but this is basically what happens. Fetch, decode, execute, fetch, decode, execute. We fetch from the program counter's address, and unless we do one of these control instructions, PC is just incremented after each instruction. But this changes when we have an interrupt. So when an interrupt occurs, the next fetch is going to be not from what the PC was before the interrupt, but it's going to be from a special location. It's going to be from location 8 or 18 in the program memory, depending on whether the interrupt is low priority or high priority. And the program counter that would have been used to do the next fetch is saved on the stack. So the interrupt basically causes a call to location 8 or 18. Okay, so that concept is relatively straightforward. There's a lot going on there, but basic idea, an interrupt basically does a call to one of these locations. That in itself is not that different from things that we've been talking about. The real challenge in working with interrupts is setting up the interrupt subsystem. For example, you need to turn on these bits in the intcon register. If you want an interrupt to come from, say, the pin int 0, you need to turn on int 0 interrupt enable. And when you get an interrupt, you can check int 0 interrupt flag to see if that interrupt came from int 0. And when you're done processing the interrupt, you clear this bit so that you don't immediately get another interrupt as soon as you re-enable. And other interrupts have different registers. For example, intcon 3 is used to enable int1 interrupts or int2 interrupts, and to check int1, int2 flags, and to set the priority of int1 and int2. And so you have this whole data sheet of registers that you need to pay attention to, largely for dealing with interrupts. And this is the part that's going to be similar when we start talking about what we're going into next, which is the timing subsystem. So what's the idea of the timing subsystem? Kind of the same thing as an interrupt. Think of an interrupt like this. Normally we fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. We keep going down through successive locations in memory, or we follow branches and calls and so on. But when this event occurs, such as putting 5 volts on an interrupt pin outside the PIC processor, we change that fetch piece of the fetch, decode, execute cycle, and we say, hey, I want you to go ahead and fetch from somewhere else in memory, from location 8 or location 18. Okay, this is what a timer does. A timer is another subsystem inside the PIC processor. So we're talking about timers. And there's 4 timers, 0, 1, 2, and 3. We're going to talk pretty exclusively about timer 0 to begin with, but most of the other timers are basically the same. Timer 2 has some peculiarities, but if we understand timer 0 very well, we can easily understand timer 1, 2, and 3. So we're going to talk about timer 0 in particular. And here's the high-level behavior of timer 0. Just like an interrupt, which we set up, we arm the interrupt system, right, by setting these enable bits and so on. We arm the interrupt system so that later something happens that causes this change in the fetch, decode, execute, causes this call to location 8. With timers, we set up the timing subsystem, we arm it, so that at some point in time later, the same thing happens. We can cause the system to make a call to location 8 or 18 by triggering an interrupt from the timing subsystem. Okay, so an interrupt by itself that we've been talking about is triggered by raising or dropping a voltage on an input pin. One of these int 0, int 1, or int 2 pins, right? With the timing subsystem, what we do is we specify a certain amount of time, a number of microseconds or milliseconds, and we say, okay, count off that much time in the back of your head, right? And when that much time has passed, go ahead and generate an interrupt. And then that interrupt, through the magic of the interrupt system, will cause a call to location 8 or 18, temporarily suspending the usual fetch, decode, execute that we were doing from successive locations. So the timing subsystem is all about 1, setting a time interval, 2, arming the system. So saying, okay, start your timer, and here's what I want to have happen when the timer expires. And then 3, responding when the timer expires. Okay, so go back and read that, listen to that again, and look at your notes on it and think about it some more. High-level setup, right? We're going to set up a timing interval, right, inside, say, the timer 0 subsystem. We're going to say, okay, your timing interval is going to be 2.5 seconds. And then we're going to arm the system. We're going to say, okay, start timing. And then 2.5 seconds after that, whatever we're doing, we're going to get an interrupt from the timing subsystem. And assuming that we don't have interrupts turned off, assuming they've been turned on, we're going to find ourselves at location 8 or 18, high priority or low priority interrupt. And we can know that since we're at this location, 2.5 seconds must have passed since we armed the system. So it's a way to set up a delay and say, I want you to go do something once this much time has passed. Okay, so we're going to come down a little bit lower level detail. How does this work? Well, there's an oscillator inside the computer, like all computers. The internal oscillator by default is running at 32 kilohertz. It's a very slow clock compared to, 2.5 gigahertz modern laptop. 32 kilohertz, okay? And this, for technical reasons, gets divided by 4. So 8 kilohertz, this is what we call the instruction clock. This means we do 8,000 instructions per second, okay, which is even slower. So basically 8,000 instructions per second. And that's the real kind of heart of our time base. Okay, we're going to think of things in terms of instructions per second. Well, here's how this whole set a timing interval, arm the system business works. We basically load a value into a register called timer 0. and this can be 8 or 16 bits. But we load some value into that, and then we say, okay, go ahead and start incrementing this timer 0 register. And we increment every 8,000th of a second. Why every 8,000th of a second? Because there's 8,000 instructions per second. Ergo, every time an instruction executes, we increment the value of this timer 0 register. And then the last thing is, when this register overflows, request an interrupt. So this is the main thing that we're going to do, the lower level detail of how we're going to work with the timers. We're going to calculate how many 8,000ths of a second we want the system to wait. And then we're going to say, what value should we load into timer 0 so that after that many 8,000ths of a second, this register will overflow. So it's a little trickier than just counting down. We're actually counting up until it counts as high as it can, and then the next tick, it will overflow, and that will be the event that requests an interrupt. Okay, so let me give you a fairly simple abstract example. This is not what's actually going to get done. But suppose we want to wait 1 second. Well, we want timer 0 to be 16 bits, and we want to load this number into timer 0. 65,536 minus 8,000. Why this number? Because that's the overflow point, right? 65,535 is the largest value you can put in a 16-bit register. So when we reach that value and we tick once more, the register timer 0 will overflow and we'll get our interrupt. So by loading 65,536 minus 8,000, right, we know that after 8,000 ticks, this register will be up to 65,536, which is basically 0, and an overflow will have just occurred. And why is it 8,000? Because that's the number of instructions that can be executed in 1 second. And how do we know that? Because one instruction equals 1/8,000th of a second. Okay, that's a sort of medium level view of how the timing subsystem works. So think about that some more, right? Every 8,000th of a second, an instruction executes. When an instruction executes, timer 0 is incremented. When timer 0 overflows, we get our interrupt request. So if we want to wait 1 second, we could load this value into timer 0, and after a second, timer 0 will overflow. If we want to wait 2 seconds, we could load this minus 2 times 8,000. And if we wanted to wait 4 seconds, we could load this 65,536 minus 4 times 8,000 into timer 0. And these numbers are getting smaller and smaller, right? Which means it's going to take longer and longer for the overflow to occur. If we start off at this, and this is some number around 32,000, it's going to take roughly 32,000 ticks before this register overflows, and we're getting 8,000 ticks a second. That's going to be 4 seconds. Okay, so you want to try to really understand that level of abstraction before we go into the details, because the details can be really confusing. But I don't want you to be getting too confused on this part of it, okay? If you're going to get confused, it should be on the individual bits and some of the funny arithmetic involved. But make sure that you understand this part. And next video, let's talk about the actual details at the bit level.